In this video, we are going to look at problem 3694, distinct points reachable after substring removal. So here we are going to use linear scheme, and both the time complexity and space complexity of our solutions will be O of n, in other words linear, where n is the length of the string S. So in this problem, it requires that we remove every possible length k substring from S, and then starting from the origin and perform the remaining moves in order. And what we want to return is the count of distinct final coordinates reachable, right? So if you look at the three examples, example 2 is very special because here k is equal to the length of the string S. Therefore, after you do the removal, so you have an empty string. So therefore, you can only stay at the origin. This is the return for 1. Well, in the third example, so the string S contains a unique character U. And then if you move any one of them, you still get the same string. Therefore, the output is 1. So example 1 partially represents the generic case. So here, if you remove the first L, you get UL. If you move the middle U, you get 2 L's. If you move the last L, you get LU. So actually LU and UL give you the same final points. Therefore, there are 2 distinct points given here, right? So the constraints are the following. First one is the size, right? So the length of the string S can be as long as 10 to the power 5. And therefore, we need to pay attention to the time complexity of our coding. And the second one and the third one are both consistency assumptions, right? With that said, we want to move to the coding part. So, but before we do that, I want to point 2 points and the overall plan. So first is the cancellation property between the pairs R and L and U and D's. For example, if you have 3 L's and 2 R's, the final result will be 1 L. Similarly, if you have 4 R's and 2 L's, the final result will correspond to move to the right twice, right? So this is the one point. The second point is that we care only about the number of different locations, right? The number, the count, not the actual locations. So this is the second one. So our plan will be the following. First, we are going to give a solution which is longer, but for digestion, right? The second one, it will be based on the second points. We are going to get a succinct solution, right? So here, actually in version v2, we used some invariant property. So with that said, we are ready to look at the coding. So first, I'm going to get the count of UDLRs. So count S, you can print out that. So for example, so you get 2 L's and 1 up, right? So now what we want to do is this. First, I'm going to delete the length k substring at the very beginning. So for I in range k. So what we are going to do is ds corresponding to I is decreased by 1. Then you can then print out the d again, right? So here d have 1 L and 1 U, right? So what we want to check is we want to represent the state by a length 4 tuple, right? So here the tuple will represent the UDLRs, the effective ones, after using the cancellation property. So here let me write a hyperfunction at the very beginning. Or you can write it as a method in this class, but I guess writing here should be enough, because the logic is very simple. So I'm going to get a state, so given a dictionary state, and then we are going to represent the U and D, L, R, right? So first, let's initialize it. So 0, 0, 0, 0, right? And then if D, let's get the number of ups. So if this is less than the number of downs, right? So then we are going to set the first, the index 1 element. So state at index 1 is going to be this one minus this U, right? So otherwise, So we're going to set state 0 to be actually the negative of this guy. Let me write like this. So same for the L and R, right? If the number of L's is less than or equal to the number of R's, so the effect will be have some R's, right? So we're going to set state, so -1. -1 corresponding to R. It's going to be the difference of these two. Minus this one, right? So otherwise, so we're going to set state -2. That's corresponding to L. So it's going to be negative of this this one, right? And then what we want to return is a tuple of this state. The reason we return as tuple is due to the fact that we are going to use set. So tuple can be used as a set element. So for example here, if you look at the status, so get state D, let's print it out. So what you get will be this. So one up and one left, right? So now what we want to do is this. So we initialize a result, which is a set, and then let's first add this current state into that get state. So D, and then what we want to do is this. So in the rigorous sense, we can also add 0, 0, 0, 0, because originally we are at the origin, right? But this is a small point. So we're going to do some simulations. So for I in range k length s. So what we want to remove is remove this one. Remove s. So any at index I, and then here I minus k plus 1, right? So the length of this from this index to I is k, right? So if we want to remove this, it corresponds to dsi, so decremented by 1. And then we need to add back si minus k. So dsi minus k is incremented by 1. And then this decrement state will give us new state. So we can do this. Result add get state D. So what we want to do is to return the length of this result. So we can first check it. Let's see. Still here, I guess it's still to this one. We cannot add it, right? Yeah. So we get this one, and then we can submit. Yeah, it passes all the cases. So here you can print out this D, print out this result, so you can see track the final status. So here for case 1, for example, it corresponds to move to the left twice, correspond to this point, and this one corresponding to this point. Similarly for other points, right? So with that said, this is the first version, which is longer, but here we are using a for tuple to represent the final state, and then we get the counts. So here the results, the tuple in the result set correspond to exact final points, but we don't need that based on point 2, right? We care only about the different number of different locations. So this enables us to write another solution. So here, let me write here. So I'm going to use this one as version v1. So first, what we want to do is this. So we can map the U like up, it corresponds to this one, down corresponds to 0, -1, and L corresponds to, so move to left, so R move to the right, so corresponds to 1 and 0, right? So once you have this, so we can try to use a 2 tuple to represent the coordinates, right? And then what we are going to do is make a set, let's call it, right? And then originally we are at this position, right? So then what we are going to do is to mimic the positions. So what we do is for So x, it's not for I in range, so k length s, right? So here actually this thing will what we store in this one will be the relative position. So originally if you do nothing, so you get corresponding to this say 0 0. So let me write it like this, right? So what we do is that, so it's corresponding to do this part, right? So but what we want to do, get the current direction is corresponding to moves si, right? And the previous one will be pdx pdy will be moves si minus k, right? So the overall result of this two will be x in increment d in dx minus in so and current x minus previous d delta x. So same for y, and dy minus pdy, right? So this xy gives a new state. So we're going to add this, right? And then finally, again, we just need to return the length of the state. So we can do a test. Yeah, it passes all the cases in a fast fashion. So here there are several points I want to make. First is this. So here we have a sin. We add a 0 0 at the very beginning, but here we shouldn't add, right? The reason is that we have add this one. This is the original location, and this at this state corresponds to the exact location. Therefore, we don't need. And this one 0 0. Here the sin starts its relative location. That's why we add a 0 0 here. So this one is corresponding to this one here, right? So another one is that you notice that we didn't do something like this here, right? We directly do the from k. The reason is based on this one. So we care about the count, not the actual points. Therefore, the first removal will put the points into some other locations, but then moving from there, you are going to reach to different locations. It's corresponding to a coordinate shifts, but the shifts and the effective strings after the removal gives the same number of destination points. Not, in other words, this is invariant, the count of the final locations, right? So this is the what we used to write this code. So you can see actually if you print out this thing, it's not corresponding to the exact point, right? For example, this one corresponds negative 1, 1, and negative 0. Well, here, did I? So I guess here, let's see, yeah. Print theme. Did I got it? Oh, this is case 1, right? So these are the coordinates, not the exact coordinates, but the count will be the same. So with that said, I guess that's about it for the coding part. So if you want to do practice, might be the first version is the one you are going to write. Well, if you think slightly deeper, the second one is the preferred one, right? So with that said, thank you for